So when we have recurrence relations, what we often want to do is find solutions to those recurrence relations. And to find a solution to the recurrence relation means to find a description of all the elements of the sequence that is not recursive, doesn't require any of the previous elements of the sequence. First, I want to talk a little bit about how we kind of explore to get solutions to recurrence relations. And then I want to talk about how we prove that a solution to a recurrence relation is indeed the solution. So, in order to find solutions to recurrence relations, the method that we're going to focus on in this class is pretty simple. It's the guess and check method, and both the guess and the check are very important here. So what we're going to do is we are going to look at a recurrence relation. We're going to compute some terms using the recurrence relation, and then we're going to see if we can spot a pattern. And that's really all there is to it. So here, we're going to say, hey, here's a recurrence relation. Here's our example. an plus 1 is equal to an plus 4 with initial condition a naught equals 2. So I'm going to start at 2, and then every time I construct a new term, I'm going to add 4 to it. So if we look at a1, for example, we're going to find that a1 is equal to a naught, which is 2, plus 4. a2 is equal to 2 plus 4 plus 4. a3 is equal to 2 plus 4 plus 4 plus 4. And so on. We could keep going each time we're going to add a 4. So if we look at this, we say, hey, I see a pattern. The number of 4s that I have in play here is equal to the index of A. A1 has 1 4, A2 has 2 4s, A3 has 3 4s. So this leads us to a guess. Let's guess that there's a formula for a sub n is equal to 4n plus 2. This is our guess. We don't know this yet. So what I want you to notice about this guess is that it's another description of the nth entry of this sequence that doesn't involve any previous entries. There's no a's on this side. So that's what it means to say that we've solved the recurrence relation. Another way to just say this is that we have a closed form solution here. We don't know that this is actually right yet, though. We have to also check. So we did the guessing, and now let's check. And to check, what we're going to do is we're going to take the prediction of this formula for a sub n plus 1. So the prediction of this formula for a sub n plus 1 is that we should have n plus 1 4s plus 2. So my prediction, in other words, is 4 times n plus 1 plus 2. Which is equal to 4n plus 2 plus 4. I took the 1 inside the n plus 1 here, and I just moved it out. I had to multiply by 4 to do that. And hey, guess what? I recognize this part because that is just a sub n. So what I've accomplished here is that, hey, if a sub n is equal to 4n plus 2, if that was a true description of my sequence, then I would have shown here, hey, if this is right, then it's indeed the case that an plus 1 is equal to a sub n plus 4 on the outside. So in other words, the sequence that I would generate with the formula a sub n equals 4n plus 2, that agrees with the recurrence relation I started with. It's a solution to that recurrence relation. This is not really a formal proof, but it is a little check to let us know that we have the right answer, and then we'll talk about a formal proof in the next video. For now, let's do another example here. So here we are. Here's our example. This time our recurrence relation is that a sub n plus 1 is equal to n plus 2 times a sub n, and our initial condition is a naught is equal to 1. So let's calculate a few terms here so that we can use the guess and check method. We're going to try to find a pattern. So here, a sub 1, well, here, n is equal to, this is a little bit tricky, 1 here is n plus 1. So that means n itself must be equal to 0. So n plus 2 is 2. So we have a1 is equal to 2 times a0, which is equal to 2 times 1. a1, or a2, sorry, is equal to, so now if n plus 1 is equal to 2, n must be equal to 1. So n plus 2 is 3 times a1. And we know that a1 is 2 times 1, so this is 3 times 2 times 1. Let's do one more, a3. Okay, so now it's going to be 4 times a2, which is equal to 4 times 3 times 2 times 1. So around here, we might have a guess, hey, it looks like the factorial function is involved somehow. So let's make a guess. Maybe here we have to kind of do a little bit of careful bookkeeping. A3 looks like it corresponds to 4 factorial. So that means for my guess, I'm going to say, hey, maybe an is equal to n plus 1 factorial. We don't know that yet. Is that true? Let's check. If we consider our formula for an plus 1, according to this guess, then if we plug in, we would find, okay, this is n plus 2 factorial, that's my guess, and that is equal to n plus 2 times n plus 1 factorial by factorial properties that we've seen before. And hey, n plus 1 factorial is equal to my guess for an. So that would be an plus 2 over here times an, and that indeed agrees with my recurrence relation from before. So with the guess and check method, we just look at a few entries and then we try to find patterns. We can often, not always, but often, get some reasonable solutions for recurrence relations. There are systematic methods for finding solutions to recurrence relations. There are formulas that work for recurrence relations of specific forms. We're not going to focus on those too much in this class. Instead, we're going to focus a little bit more on how to prove the solution to a recurrence relation once you've found it.